Hello YouTube and welcome back. This is a continuation from the previous video that I uploaded, and I just want to thank you for your support. This is George the Scientist. We're back with Astronomy and Cosmology. This is brand new material from the CAIE syllabus. A lot of you have been writing and supporting and asking whether we can have a session where I'm able to solve some questions. Well, you go. Now, we have some facts which I'd like you to please think about, and these are just equations which CAIE might give you or might not give you as a student. So you need to know what a light year is, and I'm just going to keep writing on my screen here, for you to see. That is how you calculate the light year. So the light year is converted into a distance there. The radiant flux intensity is the ratio between the power of the star and the surface area of the sphere, right? And it's denoted by the letter F. When we talk about the radiant flux intensity, this is basically the power of the star, but this is the power of the star when it's measured away from the star. There's a lot of confusion between the radiant flux intensity and what we call the luminosity of the star, right? So when you talk about the luminosity of the star L, this is the power of the star right next to the star, so right at the star, okay? So L is at the star, the power at the star, but when you talk about the F, which is the radiant flux intensity, this is away from the star. All right, so that's the distinction there. All right, so you also need to know about Wien's displacement law, very important. You need to know the value of the constant. We're going to talk about this later. And of course, Hubble's law and how it tells us about the Big Bang and confirms that the universe is expanding and talks about the fate of the universe, which I'm going to talk about later in the video. All right, so please like, please subscribe right at the button below there, and let's get on right and start this class. All right, so this is a test which I did with my class last year, 2021, and it's a 60-minute test, and it's just questions that are put together to give you guys sort of something which you can look at as you prepare for your exams. Question number 1, let's get right into it. The sun behaves as a black body radiator. You're given the wavelength of radiation, and that's the peak wavelength. You're asked to show, you're supposed to show that the temperature is about 6,000 Kelvin. Right, so you have the wavelength which is lambda, has been given there, and all you need to do here, because you have a temperature that you want to show and a wavelength, then it is rather obvious that we have to use Wien's displacement law here, which states that the lambda max T is equals to a constant. All right, the value of this constant is given as 2.9 times 10 to the minus 3 meters Kelvin. All right, so if you put in the appropriate numbers, you'll be able to see that T is going to be equal to K divided by lambda, and you can find your answer. You'll get an answer of approximately 5,576, which obviously, when you round off, is going to be equal to 6,000. Straightforward. What about the second one? Right, so it gets confusing here, so let's be careful here. The radiation received from the sun, this is on top of the atmosphere, all right? So if that's the radiation that's being received right at the top of the atmosphere, it means that this is the power away from the star or away from the sun. So I'm already thinking about F in this case. They ask you then to show that the luminosity of the sun is the value given there. So I will then say, because it's at the top of the atmosphere, it's away from the sun, and that's going to be the radiant flux intensity, right? So F is going to be equal to L divided by 4 pi d squared. That equation is given right up on this page. all right? And if you want to find the luminosity, therefore, make L the subject, therefore, and L is going to be F 4 pi d squared. And if you work this out, you can now see that this value of 1.37 is the power away from the sun. That's going to be your F. Of course, 4 pi is just a constant, and the distance, what do we do with the distance? All right, the distance is given here as 1.49 10 to the 11, and you will be able to get your answer. When you work this out, you'll get 3.82 times 10 to the 26. Of course, you need to put in some work into this and just confirm that these answers are okay. Another easy question, 2 marks. All right, let's keep moving. Hence, calculate the radius of the sun, right? So if we want to talk about the radius of the sun, we are right now at the sun. So if you are at the sun because you're finding the radius of the sun, then L is going to be 4 pi phi r squared t to the 4. All right, so we are at the sun, we're talking about luminosity. Sometimes this is given as a symbol with an L with a little dot there. All right, that's the same thing as luminosity. All right, so what do you do here? Make R the subject of the equation, and R is going to be L over 4 pi phi t to the 4. All right, so you need to work this out. You already have your L, and where's your L? Well, you just found it. This is your L, okay? And of course, you have your 4 pi, and you have phi there, t to the 4. Remember, the value of this thing, the symbol here called phi, is also given as, or we can find this, as 5.67 times 10 to the negative 8. Of course, you know that T is equals to 6,000 Kelvin, and it's a thermodynamic temperature. And if you work this out, you will see that R is going to be 6.58 times 10 to the power of 8 meters. All right? Excuse my handwriting there. All right, so you need to put in some work onto this, and just be able to find out how to work this out. So these are 2-mark questions. If you see a 2-mark question in CAIE, that should be a straightforward calculation question. It should not be a problem at all. All right, so let's move on to the next. Now, the next question involves a graph, all right? So this is a graph of log P, against log T. And it's a beautiful question because what it does is it tells you that P is related by T using the equation there, and they ask you to find the value for N. Well, I think this is rather obvious, and you can use the same skill when you're solving paper 5, question 1, which is the planning question, because you're going to get such graphs and they'll ask you to evaluate the relationship, etc. So obviously, if we have log P on one side, this is going to be equal to log K plus N log T. You can see now that because this is a straight line graph, we can see that there's a corresponding case here, and log P is going to be Y, and Y is going to be equal to, all right, so that's going to be, let me just hold on to that log K. I'm not going to tell you what it's going to be, but you can see that it's against log T, which is your X. Well, if that's X, then this has got to be M because it's a straight line graph. We're looking for Y is MX plus C, or Y is MX plus B, as some would say. And this is definitely going to be my C. So I can now see that obviously N is actually the value of M, i.e., that is the gradient. So all you need to do is look back at your line and work out the gradient. All right? And if you work this out, get a minute again, put in some work, and work this out. N is going to be change in Y over change in X, and you can see that if you work it out, you're going to see that N is going to be equal to 4. All right, so put in the work and get the answer and confirm my answer. All right, comments below if you have any question about how I get these answers. All right, put in the work. Okay, you're the student. Okay, number 3, let's keep going. We've been given the value of the Hubble constant. Now remember, they say it is thought to be. All right, so the Hubble constant does not have a constant value, although it's called a Hubble constant. It is a conundrum right there, because the Hubble constant is an estimated constant. All right, and the reason for that is because when we observe galaxies, we do not get a line. When you draw a line on the graph I'm going to show you in a minute, this is a graph of V against D, you know, the receding speed of the galaxy against how far the galaxy is from us. We do not always get a straight line. So if we have a graph of V against D, remember V is the receding speed and D is the distance from the galaxy, from the observer, who is us on the Earth. We get a scatter graph, all right? Now, if we get a scatter graph, then we can only draw a line that looks that way, and from that line, we can be able to get the Hubble constant. So it is an averaged constant. So it's thought to be about that value there. Now, give one reason why the value of this constant is uncertain. Well, remember this. The Hubble constant is found by V divided by D. All right? And this means this is the speed of recession. So this is the recession speed. Recession means how quickly it's moving away from us. So this is the recession speed. And we're dividing the recession speed by the distance, and this is the distance from the observer, and this is the distance from us. All right? So if you do that, you'll find the Hubble constant. However, it is uncertain because the universe is expanding. All right, now listen to me carefully here. The universe is expanding. And if the universe is expanding, it means that D, the distance from us, is constantly increasing. All right? So because D is constantly increasing, we have a slight problem, because it means that when we go back to the graph, which I gave you at the start of V against D, you see that different galaxies will have, or will show, different positions within the V against D graph. So for example, this point represents galaxy A, and this point would represent galaxy B, and this point would represent galaxy Z, etc. Now, all these points here are really just an average of the line that we have drawn. All right? Now, because these are just a representation of an average of the line that we have drawn, because when we draw this line and we find the gradient of this line, we're going to find V, change in V against change in D, which is going to give us the Hubble constant. It shows you that because not all galaxies fall on the line here, the value is rather uncertain. And that's the way you answer this question. All right, so it's a 1-mark question. I've made it really wordy. The 1-mark answer would simply be that the ratio between recession speed and distance from us gives the Hubble constant. However, on the graph of V against D, we see that not all the galaxies, or very few galaxies, actually fall on the average line that is drawn. Therefore, the Hubble constant is simply an average constant, and it is not certain. So it is really just a value that's thought to be what we say it is. All right, let's try and handle the next one. State how an estimate of the age of the universe, can be calculated from the Hubble constant. All right, another 1-mark question here. Right, so we know that the speed is equals to distance over time. Okay? If speed is distance over time, the average speed of a galaxy that's receding from us is given as 2.1 times 10 to the 7. These are values that are given by aeronautical and space agencies, and that's what I'm using here. All right, so that's the speed. And we also know that the distance from us to the nearest galaxy is around 9.5 times 10 to the 25 meters. So looking at those two values, you can be able, therefore, to find t. Now, this t is the time since the Big Bang happened. All right? The time since the Big Bang happened is the age of the universe. So quickly, if you do d over s, you will be able to see that you get an answer of 4.52 times 10 to the power of 18 seconds. All right? And this gives you an average of about 14 billion years. So yes, we can actually say that the universe is estimated to be around 14 billion years, and we can use the theory or the understanding of the Hubble constant to be able to explain this. All right, what about C? Explain how the ultimate fate of the universe is associated with the Hubble constant. Well, what is the ultimate fate of the universe? The universe that we live in is expanding, all right? So what we see in the universe is planets, we see light, we see, and I'm talking about visible light in this case, we see stars, etc. So we know that these galaxies are expanding, they're moving away from each other. So the fate of the universe is that it has enough matter, and this matter includes dark matter and gravitational attraction. And what's going to happen is, if the universe is expanding and getting bigger and bigger and bigger, gradually, because there's so much matter, physical matter and dark matter, this matter will eventually be able to gradually halt the expansion of the universe. All right? So the ultimate fate of the universe is that the expansion is going to be halted. All right? If the expansion of the universe is halted, then what's going to happen? Well, what's going to happen is that we're going to have a crunch. We're going to have everything in the universe collapsing into each other. So when the expansion is halted, this is going to precipitate, okay, it's going to precipitate the collapse of the universe. Okay, so this is the ultimate fate of the universe. The universe is going to collapse because of the amount of gravity and matter that is inside it. So how is this associated with the Hubble constant? Well, remember that the Hubble constant is calculated by V over D. So if the Hubble constant is to stay constant, it means that the ratio between V over D has to also stay constant, which means that V is going to get very, very small. The speed is going to get small because, remember, the expansion is going to halt. And ultimately, the distance is also going to get very, very small. And when this happens, you can see that the value of Hubble constant, for it to stay the same, if these two values get very, very, very small, then it's almost impossible to have a value for the Hubble constant. All right? So we say that the fate of the universe is that it's going to collapse. 4a. This is probably one of the easiest ones. Okay, we have a planet, and the mass is m, and it's orbiting a star of a bigger mass m. Right. So the radius is given as r. They want you to find out or derive this equation here. Okay? I think this is pretty simple. We do the same in gravitational fields. Of course, we know that the force of gravity is the same as the centripetal force. All right? That's the first thing you need to remember. And when I talk about force of gravity, I'm talking about G m over r squared to be equal to mv squared over r. All right, you remember that from gravitational fields. But also we need to remember something, that distance is speed times time. Now remember, this is circular motion. This is not, or circular distance, sorry. It is not a linear distance. We're going to use a linear equation because this is just tracing the path of the mass m as it moves around. So we know that t is distance over speed, And t, therefore, because it's a circular distance, remember it's a circumference, is 2 pi r over the speed, which is v. We're talking about a linear speed here, all right? You will then simply use these two equations here to solve this. All right, so what does this become? This becomes gm over r is equals to 4 pi squared r squared over t squared. Okay, now how did I do that? Well, what I did is that I made v the subject, and when I make v the subject on this side, well, make v the subject on this equation, my apologies, and you bring it onto this bit, you'll end up with this equation, and that's going to give you your value for t squared. All right, put in the work and see whether it works or not. It definitely will work. Okay, I'd like us to finish this. Measurements have shown that that star has a planet which orbits the star with a period of about 6 years. All right, and the radius of the orbit is 3 times the radius of the Earth's orbit around the Sun. So what do they want us to do here? They want you to use the formula above to determine the value of that ratio there. This looks difficult, but it's extremely simple. All right, so look, the time period is 6 years, all right? And the radius of the orbit is 3 times the radius of the Earth. Okay, remember on the Earth, the time period is 1 year, and the radius of the orbit is just RE, which means radius of the Earth, okay, or radius around our star, okay, which is, I'm just going to call it RE. Now, looking at the equation above, I'm going to make m the subject because we're trying to find ratios of m's. Therefore, I could say that m is going to be equal to 4 pi squared r cubed over t squared. Okay, so we're going to use this ratio, okay, to find the mass of the star and divide it by the mass of the Sun and find our final answer. So all you need to do really is to have 4 pi squared for the mass of the star. The radius is going to be, for the star, is going to be 3 RE, remember it's cubed, and you're going to divide that by t squared, which is 6 squared, and that value there is going to be divided by RE, remember that's cubed, and that's just going to be 1 squared. Well, work it out and see what you get. I think you're going to get 0.75. This is going to be the last question I'm going to do for today, and I'm going to post another video following this on some more work on astrology and cosmology, so please make sure you check it out. All right, so because of the presence of the planets, the star does not remain at rest. No, it doesn't. Remember, a star is very fluid. It's a ball of gases. Instead, the planet and the star both orbit around their common center of mass. Explain why the orbiting speed of the star is very small in comparison to the speed of the planet. Well, think of it this way, all right? So what we have is we have a planet, and this is the planet, which is going in an orbit, in this orbit here. And right here, we have the star, all right? And the center of rotation for both the planet and the star is right there. But remember, the star is a ball of gases, all right? So this star is also rotating, okay? So it is rotating with its center right there. So look at the question. The question is saying to us, can you explain why the orbiting speed of the star is very small in comparison to the speed of the planet? Well, look at the distances. The distance from the center of rotation to the planet versus the distance from the center of rotation to the star. And you see that if I call the distance from the center of rotation to the planet r, then I'm going to call the distance from the center of rotation to the star small r. And what do you see? You see that small r is much, much smaller than big R. all right? And so for that reason, because we know the star is a ball of gases, it does not just stay at rest, it's not a solid rock, all right? So the star is spinning and the star is rotating, and if they're sharing a common center of mass, then it means that the bit that is closer to this center is going to move faster than the bit that is farther away. And that's the reason, basically. So with that reason, you can say that the one that is closer to the center of rotation is going to move faster. It moves faster. Well, why does it move faster? Well, because we know that if the distance from the center of rotation is smaller, then the object is supposed to cover the circumference that it's moving through a little faster than when the distance is farther away. So because the planet is much farther away, it takes more time to do that whole wide big circle compared to the star, the edge of the star, or the particles in the star that are rotating, that are pretty close to the center, which is the one we're using for both the planet and the star. All right? I have many more questions to carry on with. I'm going to put these on to my next video. I'd just like you to think about these, mull over them, and let's talk about them. All right? So please subscribe, and please listen, and please learn. I'm going to post a lot of videos just before the exams coming up in the next couple of weeks. All right, thank you very much, YouTube. Thanks for your support. This is George the Scientist signing out. I will see you guys soon.